Whenever we think about the smartest individual who ever lived, we always think about him. But the truth is, even Albert Einstein may agree that Isaac Newton could be, or maybe even was, smarter than him. Some famous scientists and social media personalities share this view. Here's a sample clip of how Neil deGrasse Tyson responded in an interview at the 92nd Street Y, New York.
Who do you think is the most extraordinary scientific mind that that humanity has produced?
There is no contest. Isaac Newton. Nobody comes close.
Explain why.
Stay close, as you'll learn why and how he did it in detail. Before turning 26, Isaac Newton made groundbreaking discoveries in multiple fields, laying the foundation for modern physics and mathematics. Here are some of his key contributions before 1668, when he was 25. 1. 1665 to 1666, Newton developed early forms of calculus, which he called the method of fluxions, to describe changes in quantities over time. His work laid the foundation for differential and integral calculus, independently developed by Leibniz later. 2. Laws of motion and gravity, 1665 to 1666. During the Great Plague of London, 1665 to 1666, Newton retreated to his home in Woolsthorpe and formulated early ideas on motion and gravity. He conceptualized that the same force that pulls objects toward the Earth also governs planetary motion. 3. Optics and light, 1666. Newton conducted experiments with prisms and discovered that white light is composed of different colors. He established the foundation for the wave-particle theory of light. 4. The reflecting telescope, 1668. To overcome chromatic aberration in lenses, he invented the reflecting telescope, using mirrors instead of lenses. This design revolutionized astronomy and is still widely used today. 5. Binomial theorem and algebraic contributions, 1665. Newton generalized the binomial theorem for any exponent, providing a key tool for algebra and analysis. By the time he was 26, Newton had already laid the groundwork for many of his most famous later works, including the Principia Mathematica, 1687. His early years were remarkably productive, marking him as one of history's greatest scientific minds. The story of how Isaac Newton discovered calculus. Isaac Newton's discovery of calculus was a result of his deep curiosity about motion, change, and the nature of the universe. His work was largely driven by his desire to solve complex problems in physics and mathematics, problems that existing methods couldn't handle. The Plague Years, a time of isolation and genius. In 1665, the Great Plague of London forced Cambridge University to shut down. Newton, then just 22 years old, returned to his family home in Woolsthorpe, where he spent the next 2 years in isolation. This period, often called Newton's Annus Mirabilis, miraculous year, became one of the most productive times in scientific history. During this time, Newton pondered fundamental questions about motion, curves, and rates of change. Mathematicians of the time used algebra and geometry to study these topics, but their tools were insufficient for describing how things changed continuously. Newton needed something more powerful. The problem of change. One of the biggest challenges Newton faced was understanding instantaneous motion. For example, if you watch an apple fall, its speed changes continuously. How do you measure its exact speed at any given moment? Similarly, how do you determine the slope of a curve at a specific point when it's always changing? Newton realized that existing mathematics wasn't enough, so he developed a new mathematical framework that allowed him to analyze continuous change, what we now call calculus. The method of fluxions, Newton's calculus. Newton called his version of calculus the method of fluxions. He imagined quantities, like position, speed, or area, as flowing and changing over time. He introduced the concept of derivatives to measure how fast something changes, and integrals to determine the total effect of these changes. For example, if you know the speed of an object at every moment, you can calculate how far it traveled, integration. If you know an object's position, you can determine its speed at any instant, differentiation. Application to gravity and motion. Newton's calculus was not just theoretical. It helped him develop his famous laws of motion and universal gravitation. He used calculus to prove that planetary orbits followed elliptical paths, a groundbreaking result that explained Kepler's laws. Newton versus Leibniz, the controversy. Although Newton discovered calculus in the mid-1660s, he didn't publish his findings immediately. Meanwhile, the German mathematician Gottfried Wilhelm Leibniz independently developed his own version of calculus in the 1670s, using a different notation. When Leibniz published his work first, a bitter dispute arose over who had priority. Today, we recognize that both men contributed to calculus, but Leibniz's notation, using T for integration and D for differentiation, is the one most commonly used. Legacy of Newton's calculus. Newton's development of calculus revolutionized science and mathematics. It became the foundation for physics, engineering, and economics, influencing everything from rocket trajectories to modern AI algorithms. And the most astonishing part? He figured it all out by himself, before turning 26. How Isaac Newton discovered the laws of motion and gravity. Isaac Newton's discovery of the laws of motion and gravity was a result of years of deep thinking, observation, and mathematical analysis. His work fundamentally changed how we understand the universe and laid the foundation for classical physics. The Plague Years, a time of isolation and discovery. In 1665, the Great Plague of London forced Cambridge University to shut down, and a 22-year-old Newton returned to his family home in Woolsthorpe. This period, 1665 to 1666, often called Newton's Annus Mirabilis, miraculous year, was when he made some of his greatest discoveries. During this time, Newton developed early ideas on calculus, conducted experiments with light and optics, formulated the laws of motion, conceived the idea of universal gravitation. The famous apple story. How Newton thought about gravity. Legend has it that Newton was sitting in his garden when he saw an apple fall from a tree. He started wondering, why do apples always fall straight down? Does the same force that pulls the apple to the ground also extend into space? Could this force be responsible for the motion of the moon and planets? While the apple story is likely exaggerated, it does reflect Newton's thought process. He was trying to understand why objects fall and whether this force applies to celestial bodies as well. The three laws of motion. As Newton studied motion, he formulated three fundamental laws, which he later published in his 1687 book, Philosophiae Naturalis Principia Mathematica, The Mathematical Principles of Natural Philosophy, or simply Principia. First law, the law of inertia. An object at rest stays at rest, and an object in motion stays in motion with the same speed and direction unless acted upon by an external force. This means that objects don't change their motion on their own. Something must push or pull them to speed up, slow down, or change direction. Example, a rolling ball on a smooth surface will keep moving unless friction or another force stops it. Second law, the law of acceleration, F equals ma. The force acting on an object is equal to its mass multiplied by its acceleration. This equation, F equals mass, explains how forces affect motion. The greater the force applied to an object, the more it accelerates. Similarly, a heavier object requires more force to move than a lighter one. Example, pushing an empty shopping cart is easier than pushing a full one. Third law, action and reaction. For every action, there is an equal and opposite reaction. This means that forces always come in pairs. If you push on an object, it pushes back with the same force in the opposite direction. Example, when you jump off a boat, you push the boat backward as you move forward. The universal law of gravitation. Newton took his ideas further, realizing that the same force that pulls an apple to the ground also governs the motion of the moon and planets. He proposed that gravity is a universal force acting between all objects with mass. This equation explained why planets orbit the sun and why objects fall to Earth. How Newton proved his ideas. Newton combined his laws of motion and gravitation with the work of earlier astronomers like Johannes Kepler and Galileo Galilei. Kepler's laws showed that planets move in elliptical orbits. Newton used calculus to prove that his law of gravity could explain Kepler's laws mathematically. His discoveries revolutionized science, replacing centuries of Aristotelian physics and leading to modern mechanics. Conclusion. Newton's genius before age 26. By the time Newton was just 26 years old, he had already laid the groundwork for calculus, optics, and the laws of motion and gravity, all by himself. His insights shaped physics for the next 3 centuries, proving that one man's curiosity and genius could change the world. Isaac Newton's discovery of optics and light. During his years of isolation, 1665 to 1666, Isaac Newton conducted groundbreaking experiments with light and prisms. He directed sunlight through a glass prism and observed that white light split into a spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. This experiment proved that white light is not pure but made up of different colors, contradicting earlier beliefs. Newton further discovered that passing the colored light through a second prism recombined it into white light, proving that colors are intrinsic properties of light, not modifications of it. His findings revolutionized optics, leading to the development of his reflecting telescope, which used mirrors instead of lenses to eliminate color distortion. These discoveries laid the foundation for modern color theory and optical physics. Isaac Newton invented the reflecting telescope in 1668 as a solution to the problem of chromatic aberration in refracting telescopes. In refracting telescopes, lenses caused colors to blur, distorting the image. Newton realized that using a curved mirror instead of lenses to focus light would eliminate this problem. He designed a telescope with a concave mirror to gather and reflect light to a focus point, creating a clearer image. This was the first practical design of the reflecting telescope, which he demonstrated successfully. Newton's development of the reflecting telescope was a groundbreaking moment in the history of astronomy. Before him, telescopes primarily used lenses, refracting telescopes, but they had a major flaw: chromatic aberration. This distortion caused different colors of light to focus at different points, resulting in blurry images, especially for distant objects like stars. To address this, Newton applied his deep understanding of optics and light. He realized that mirrors, unlike lenses, do not suffer from chromatic aberration because light reflects off the surface without splitting into its different colors. Instead of using lenses to focus light, he used a concave mirror to gather light and reflect it to a focus point. He also added a small, flat secondary mirror to direct the light to an eyepiece on the side. The result was a telescope that could provide much clearer, more detailed images of the night sky. Newton's design was much smaller and more practical than the large refracting telescopes of his time, and it marked a shift in telescope design that is still used today in modern observatories. Newton's reflecting telescope was a huge advancement in both practical astronomy and the understanding of optics. It proved that mirrors could be used for precise optical instruments, which led to the development of even more powerful telescopes in the centuries that followed. Isaac Newton made significant contributions to algebra and calculus, especially through his work on the binomial theorem. The binomial theorem is a formula for expanding powers of binomials, expressions like a plus b n. While the theorem had been partially known to mathematicians before Newton, he developed a more general, infinite series version of it. Here's how he contributed. #binomial theorem. In the 1660s, Newton generalized the binomial theorem for any real or even fractional exponent. Earlier versions of the theorem only applied to whole number exponents. Newton's version, published in 1671 but not fully revealed until 1696, used the concept of infinite series. He showed that for any n, the expansion of 1 plus x squared n can be written as an infinite sum. 1 plus x squared n equals 1 plus nx plus frac n n minus 1, 2, x plus frac n n minus 1 n minus 2, 3x3 plus c dots. This expansion was groundbreaking because it allowed for the calculation of binomial expansions with non-integer exponents, opening up new ways to handle algebraic expressions and leading to major advances in calculus. Algebraic contributions. In addition to the binomial theorem, Newton made several important contributions to algebra. 1. Development of symbolic notation. While not the sole creator of algebraic symbols, Newton helped to standardize and promote the use of more symbolic, abstract notation in mathematics. 2. Newton's method. Newton developed a method, still used today, for finding successively better approximations to the roots, or zeros, of a function, now known as Newton's method, for solving equations. 3. Calculus and series expansion. His work on infinite series and power series was directly tied to the development of calculus, and he used these tools to solve algebraic equations and understand motion. Newton's contributions to algebra, particularly the binomial theorem, had a profound effect on the development of mathematics, especially in the areas of series, functions, and calculus. His work laid the foundation for much of modern algebraic theory.